The topic that we're going to start today is called model selection, or also known as variable selection, because the idea is to build on some of the concepts that we've done already, and now we want to look specifically at the general problem of how do we select the most relevant and useful predictors for building a multiple linear regression model. Okay, so let's introduce this idea of model selection. Okay, so we can state it as follows. So given, so let's suppose we have a whole bunch of variables that we've recorded for each observation. So in many of our examples so far, we've been dealing with fairly small linear regression models, so just several predictors, but in some bigger applications with much data, you could have a number of predictors that number in the hundreds or even more. And so we can frame this general problem as like this. So given that we have p explanatory variables or predictors, so we want to determine and find what's the best subset of them to use for building our model. And we'll see very soon that indeed it's helpful to do a reduced model because the performance of the model, if we just throw everything in, it can hinder our ability to interpret if we throw in a bunch of irrelevant variables, and it can actually also hinder the ability of the model to make good predictions. Okay, so we're going to get into that in this section of our course. Okay, so given the variables, we want to find the subset, the subset of them. Okay, so let's suppose we're going to choose a subset of them. So let's say k, which is less than equal to, of course, the number of variables that we're starting with. Find the subset of explanatory variables. So this is related to what some terms we've used before, like taking, say, the full set of predictors and finding a reduced set of them. So let's mention that. So this is, we can think of this as a sort of a reduced model that gives us the best. Okay, and I'll have to define what we mean by best. And so, of course, we're going to have to develop some metrics for determining how do we choose and how do we decide which is going to be the best subset of variables to use as predictors for the best model. Okay, and so what are some things we consider in determining whether a model is good or not? So I'll just list some of them. Okay, so for example, so we can look at the goodness of fit. Okay, which I'll give you an example of as we start to talk about metrics. So how well does the model fit the data? Also important when we have many variables is, well, can we interpret the model? Okay, and so if we have many predictors, it can be helpful to be able to find the succinct subset of them that are the most useful for explaining the response. And so generally, if we have if only a fewer number of variables are actually needed, then the model is also easier to interpret. And interpretability is also related to a concept we talked about last time, multicollinearity. So I'll mention that in just a moment. And finally, okay, so here's some points: goodness of fit, interpretability, and also predictive performance. Okay, so what we mean by predictive performance is, okay, so we fit the model to data we have, and so now suppose we have a new batch of observations where we only have X, but we don't, and we want to predict Y. So for data that was not used to fit the model, how well can our model do in terms of predicting the response? Okay, so these are some general notions of what constitutes a good regression model. Okay, so I wanted to first, before I introduce a new material, I want to relate this concept to some things we've already looked at. Okay, so here are some related concepts that we've already seen. Okay, so the first one that's is related to this problem is we've looked at f-tests. Okay, so I want to explain how that's related. Okay, so what did f-tests do? Well, we use the change in the sum of squares when we have two models. The cases where we looked at is where one is indeed a subset of the other. Okay, so the f-tests, they compare between two specific models, typically a full and a reduced. Okay, and we specifically where we test the adequacy of a reduced model versus, so in other words, this reduced model is very much related to what we're talking about here. It's usually a subset of the full model. Subset. Also another term that's sometimes used is we say nested, because all the predictors in the reduced one are also in the full. So these are synonymous terms for describing the relationship. Compared to a full model. Relative to a full model. And so the f-test compares, you give it two specific sets of predictors to use. F-test can give us a conclusion about which of those hypotheses is plausible. And compared to what we want to do in general now is not just compare two specific models, but to find the best model out of what could be a very large set of possible models, especially when the number of predictors is high. I do also mention that so on your last quiz, I asked you to do an f-test. So on quiz number 4. The f-test I asked you to do was indeed a reduced model, and you had to, in order to do that question correctly, you would have to read and interpret carefully that why is the model that throws away two of the categories a reduced model? Well, what is included there is the fact that we essentially by taking out CS and statistics, in effect what we're doing is we're setting the effects for those two majors to be the same. So it's a reduced model in that case because the null hypothesis includes the fact that the amount of time spent on memes among CS students and stat students is the same. Okay, so that's why the last part of that quiz is indeed testing for a reduced model. So this is an example of a constraint, right, that we could test using the general framework for doing linear hypothesis tests using the F distribution. Okay, so it is. So this is just a side note. Okay, is a reduced model in part D to F. So this is one of the constraints that's imposed there. Okay. Second related concept is the one we talked about last class, which is multicollinearity. Okay, and so what was multicollinearity? Well, that's where you have two or more predictors that are quite correlated with each other, and we saw what can happen when we throw all of those correlated x's in the model. Several things can happen. We looked at how the variance of the estimates can blow up to be very large, and so we can actually draw incorrect conclusions. And I also want to mention it here because if we have a strong degree of multicollinearity, that also affects our interpretability of the model. Okay, so let's make this point as well. So this can affect interpretability of, say, your estimate, let's say beta at J. And why is that? Well, because when we interpret our regression estimates, we usually say that okay, so if two predictors are highly correlated, then our usual interpretation. Okay, so what do we usually say? We say, okay, so we change x by one of the predictors by a unit, and then this estimate coefficient beta hat j tells us how much the response changes on average. But that might not make much sense if the x's are very correlated, because the usual interpretation means we have to hold other variables constant. Okay, and so that actually is not, it doesn't make much practical sense if you can't really, in practice, change one of the predictors without affecting some of the other ones. Okay, so when the x's are very highly correlated, this interpretation doesn't make a whole lot of sense. Okay, so holding doesn't really work. Okay, when the xj is strongly correlated with other predictors. Okay, so that's an example of what we mean by interpretability. Okay, so for example, in the Python case, if we say we change the length, we say, okay, if we want to predict the fat content for a different length of Python, then we have to hold all and so the estimate would depend on holding everything else constant. But as we saw in the data, it doesn't really make sense to say we can change length by one unit without changing the other length measurement, snout to vent length. And so that interpretation doesn't really make sense when the predictors that we have in the model are highly correlated. Okay, so that's a related concept to this idea. So when we have our final model, that's why we want to ensure that we don't have a high degree of problems such as multicollinearity, because that affects the interpretation of our estimates of the regression coefficients. Okay, so two more related concepts. I want to mention r squared again. Okay, so remember that r squared is the fraction of is the proportion of variability in the response explained by the regression model. And we made a note of how R squared changes, right, when we add variables to the regression. And the key thing here is to point out that it always increases when we add variables, when adding variables to the model. Okay, and why is that? Well, it's related to the f-tests we've done. So if we throw in more predictors into our model, then the sum of squares residual has to go down because of the Pythagorean argument we made. And so if the sum of squares residual goes down, then that means the R squared must increase because you'll have more sum of squares in the regression part. Okay, so since R squared always increases when we throw in more models, so just because one model has a higher R squared than another doesn't necessarily mean that we should pick the one with the larger R squared. Okay, so this R squared will always favor picking the larger model, so we would have to develop a different sort of metric, okay, compared to R squared. The last thing I want to mention is the residual variance. Okay, so in our model we use least squares. We estimate the betas, and then after we estimate the betas, we also can compute the estimate of the residual variance. Okay, so sigma hat squared is the estimated residual variance. And so when do we use this value of sigma squared hat? Well, in a few cases. So we often use this in the f-test, because remember, sigma squared hat is also the mean square residual, and so that plays an important role in our f-tests. We also use sigma squared hat when we use the model to do prediction. Okay, so this is used for prediction. So when we built prediction intervals, so say we have a new set of explanatory variable values and we want to predict the response. So if you recall, in the formula for prediction intervals, we use sigma hat in an interval. Okay, so correspondingly, we want accurate and precise predictions for new data. We want sigma squared hat to be as small as possible. Okay, and so we want sigma squared hat to be small. Okay, so based on this point, okay, so we say we want the estimated error variance to be small, so then we can make more precise predictions. That is in fact related to the first metric I'm going to talk about, which is an adjustment on R squared. Okay, so by way of giving you a roadmap of how we're going to tackle this problem, let's give you an overview that there's two main ingredients to model selection. Okay, so the two key ingredients. Okay, so first we need what we call a metric or a criteria. Criterion. Okay, so what's that for? Well, we need to so if you're going to fit a whole bunch of models with different subsets of predictors, then we need a way of calculating a statistic or a metric on these fitted models to compare them. Okay, and we also need to be able to do that. The metric also has to account for the number of predictors that we throw into the model. Okay, so so one reason I mentioned r squared here is r squared doesn't care like how many variables we put into the model. It just keeps increasing. Okay, so r squared on its own, for example, wouldn't help us choose would not help us choose models with fewer predictors. Okay, so we need to develop some criteria that can tackle that problem. Okay, so metric for comparing different models. With potentially different numbers of predictors. Okay, so that's first thing. So we need to be able to calculate that, and we can choose a model based on the value of the criterion. And as we'll see, especially when we have many variables, so let's say dozens of potential predictors or hundreds of them, we need some sort of a selection strategy or a search strategy. Okay, so which models should we fit and test? Okay, when we have many predictors, it's actually computationally infeasible, even with with multi-core and parallelization. You can see that with the more variables you have, the number of potential models that we would have to test to do so exhaustively grows exponentially. Okay, so those are two key ingredients, and so I want to start with developing some metrics. Okay, so we'll start with examples of metrics. Okay, so this is not an exhaustive list, of course, but I do want to point out those that have historically been important and still useful, even though there's more fancy ways of doing that in modern statistics. Okay, so examples of metrics for model selection. Okay, so the first one is an adjustment on r squared. So this is why I recapped r squared first, because we have, okay, so number one, as an example of a metric, is what we call the adjusted r squared. Okay, so as mentioned, we want r squared is helpful because it explains, it has an intuitive explanation, which is the proportion of variability in the response explained by the model. So it's good for it to be large, but it's not sensitive to how many variables you put in. Okay, so one early metric that was developed is to compute an adjustment on r squared that does account for how many variables we put in. Okay, so how is it calculated? So let's give it the notation r squared with subscript adjusted. Okay, so it's 1 minus the sum of squares residual divided by, okay, so suppose we fit a model with k predictors and we do n minus k minus 1, and then on the bottom is the sum of squares total divided by n minus 1. Okay, for a model with k predictors. Okay, so what I want to compare is, just so as a side note, compare to what is r squared without adjusting? Well, the original r squared is 1 minus, can also be written, it's a sum of squares regression over sum of squares total. It can also be written as 1 minus sum of squares residual over sum of squares total. And so actually on quiz number 4, this is the relationship that you would have used to calculate r squared in the first part of the quiz. In fact, you would have noticed that you don't actually need to know the ratio. You don't actually need to know the actual values of the sum of squares residual and total. All you need is the ratio. And so from the F statistic, you would have been able to calculate this ratio and therefore get r squared. Okay, so how are these related? Well, what we're doing here is we are dividing the numerator and denominator by some degrees of freedom. Okay, so you notice in the bottom you have n minus 1, and then in the top you have n minus k minus 1. So what this does is the more predictors you put in, okay, so if you hold the sum of squares residual the same, so if the sum of squares residual doesn't change when you add an additional predictor, then that means this numerator is going to go down, okay, because so this is going to go down, and therefore correspondingly the r squared this is going to be larger because we're now dividing by fewer degrees of freedom. Okay, so this is going to be larger, and therefore 1 minus that is going to be smaller. Okay, so therefore it's going to, in effect, gives us sort of a penalty for adding predictors into the model when the sum of squares residual is not changing very much. Okay, so I'm going to let me make a note of a couple things here. So what is this thing here in the numerator? Well, this is the estimate. Okay, so this should look familiar to us, right? So we fit a model with k predictors. Okay, so if this is the sum of squares residual for that model, so this would be the degrees of freedom in the residuals for a model with k predictors. So this is the estimate sigma squared hat based on that model for a model with k predictors. Okay, and then what do we have here in the denominator is, well, what is this? Sum of squares total over n minus 1. So this is, in fact, as we've seen in homework in your first assignment, this is the variance, sample variance. Of responses. Okay, so that's how we can interpret the numerator and denominator of this expression. And so let's just show, I've kind of hand waved and said like this should be smaller than r squared. So let's just do a little bit of algebra to convince ourselves of that. Okay, so r squared adjusted can be written as, okay, so using this expression, so this ratio, sum of squares residual over sum of squares total, is 1 minus r squared, and so we have this stuff in the these dividing factors. Okay, so let's rewrite that using that. So 1 minus. Okay, so we have n minus 1, because that's in the denominator of the denominator. So n minus 1, n minus k minus 1, times the ratio, sum of squares residual over sum of squares total. So that would be 1 minus the original r squared. And so further, so let's actually, just to make it more clear, let's try to write this in terms of r squared minus a vector. Okay, so I can do 1 minus, okay, so denominator n minus k minus 1, so I can put 1 plus, so I'll need to cancel a k, so this is going to be n minus k minus 1, and then you get n minus 1, so I need a k over n minus k minus 1, 1 minus r squared. Okay, and so therefore I now expand the term, so I have 1 minus 1, so that's going to cancel out the 1, and then I have a minus r squared. And then 1 minus, what's left is 1 minus r squared times k over n minus k minus 1. And so what we see here then is that the adjusted r squared is related to the original r squared, and it has an adjustment factor based on the number of predictors. K we're including in the model, because this 1 minus r squared is positive, and this is positive, so it's r squared minus, original r squared minus an adjustment factor. So therefore, this introduces the idea of penalizing models that have too many spurious predictors. The sum of squares residual and the r squared adjusted. Yeah, so this is the general formula. So we can calculate a r squared adjusted for models with any number of predictors. So this sum of squares residual is based on the model with k predictors. So the model with k predictors is used throughout this expression. So let's emphasize this part here. So this is used for calculating this entire term. Of course, with the same responses, remember the denominator only depends on the responses. So the only part that's changing is the numerator. Okay, so this is going to change depending on what variables we're throwing in the model and how many. Okay, so this expression shows us that we get the adjusted r squared as the original r squared minus some positive factor, which depends on the number of predictors thrown in. Okay, so that's why I wanted to mention recap the original r squared, because r squared adjusted is not going to have the same interpretation as the original r squared, but it does have the benefit of capturing what happens when we throw in predictors that don't really change the sum of squares residual. So r squared adjusted can actually go down if we put in irrelevant predictors. Okay, so let me write that in words first, and I'll show you a numerical example. Okay, so intuition. So why do we define r squared adjusted? Well, so this r squared adjusted, well, accounts for the number of variables in the model. And so it penalizes having unimportant models. Okay, it penalizes the inclusion of unimportant predictors. Okay, and what do we mean by unimportant predictors? Well, let's make sure that's clear. Unimportant in the sense that sum of squares residual has little change, has little decrease when adding the variables. Adding such variables. Okay, and so compared to the r squared, it doesn't have the same interpretation. Okay, so it counts for a number of variables while the original r squared always increases with more predictors. Okay, so r squared always increases, but r squared can decrease. Not always. I mean, if of course you're throwing important predictors, then r squared adjusted will increase, but it will decrease in certain circumstances. So it can decrease if the change in the sum of squares residual so the sum of squared residual doesn't really change, in the sense that throwing in the additional predictor doesn't really reduce the residual variability, or in other words, it doesn't really impact the response. Okay, so if the sum of squares change is small, okay, and so consequently, we can think of r squared as a potential metric or criteria for comparing models. Okay, so if you fit a whole bunch of models, it would make sense. And this, based on this intuition, one way to choose your model would be to choose the one with the highest adjusted r squared. Okay, so let's point that out here. So while it doesn't have the same interpretation, so while r squared adjusted loses the usual interpretation, of r squared. Okay, so it's no longer the fraction of variance explained in the response, but the way it's defined, we can use it, but can be used as a model selection criterion. Okay, so but can be used as a first measure, as a measure of, okay, so remember the first term I used, goodness of fit. This would be an example of measuring the goodness of fit. Okay, so and model selection criteria. Okay, so you can, for example, pick the subset of predictors that gives the highest value of r squared adjusted. Okay, so that would be an example of a metric that we calculate, and so we can use it. We can compare a whole bunch of different subsets of predictors. For example, using this r squared adjusted, and we can use it as a measure of goodness of fit because it builds in an adjustment to penalize us if we throw in irrelevant predictors. So I want to illustrate that numerically so you can see what actually happens. And to illustrate it, we also see why this is actually quite intuitive, because it's directly connected to the residual variance. Okay, so I mentioned sigma squared hat, and in fact r squared adjusted is very much a function of that. Okay, but first let me show you some numbers so you can see what happens. Okay, so numerical example. So let's just see conceptually what happens. So let's say we have 25 observations, and say the sum of, so just give you some statistics. So say the sum of squares total is say 20, and we have in total we have, let's say 6 predictors. Okay, and so suppose we're considering a possible model, a subset of k equals 4 predictors, and find these statistics. Okay. Okay, so I'm just going to show some numbers so that you can see how the R squared adjusted behaves and the R squared behaves, and ultimately how does the residual variance behave. Okay, so let's make a table here. So suppose and find these values. So here is the reduced model where you have k equals 4 predictors, and then the so-called full model where you have 6. Okay, so let's make a bunch of statistics. So suppose we know the sum of squares total under these models, and we also know the sum of squares residual under these models. Okay, so sum of squares total, recall, does not change because we're dealing with the same 25 responses. So it's given here as 20, so we can fill it in. But what will change when we add variables to the model? So going from 4 predictors to 6, we already learned that the sum of squares residual, going from reduced to full, has to decrease. Okay, so let's imagine, suppose we do this regression, and we have a sum of squared residual of, let's say, 10, based on this model that we're considering, which has 4 predictors. And then when we throw in 2 additional variables, the sum of squares residual decreases, but not by a lot. Let's say it goes down to, let's say, 9.8. Okay, so it's a very small reduction in the sum of squares residual, which intuitively tells us that throwing in these two additional variables doesn't do much in terms of predictive ability for the model. Okay, and so we already learned, for example, how to do an F-test based on this change in sum of squares residual, and that's the basis of testing reduced models versus a full one on the basis of the F distribution. Here specifically, though, I want to focus on these metrics. Okay, so we can calculate, for example, okay, so I'm doing different colors. So based on these values, we can now calculate the following. So we can calculate. Okay, so let's calculate R squared first. Okay, so this R squared is the fraction variance explained. So in this case, it's just 10 out of 20. So this is 0.5. In the model with 6 predictors, then the R squared would be, so R squared is going to go up, right? Because this sum of squared residual has decreased a little bit. Okay, so this would be 10.2 over 20, or 51% of the variability. So you see that necessarily R squared can only increase when we throw in more predictors. Okay, but the point of this is to also look at what happens to the adjusted R squared. Okay, so let's also calculate that. So based on the formula that we wrote down, okay, it's not here anymore, but it's 1 minus. Okay, so it's 1 minus. Okay, so on the top, I do the sum of squares residual, and then divide by the degrees of freedom in the residual in this case. So n minus k minus 1. So 25 minus 4 minus 1. So this is 20. And then the bottom we have the sum of squares total divided by n minus 1, so 20 over 24. Okay, and so we can do so this comes out to be 0.4. Okay, and we can do the same for the full model. Okay, and we'll see how the adjusted R squared is going to penalize this full model. Okay, so what are we going to calculate now? Well, we do 1 minus. Now the sum of squares residual has gone down to 9.8. But now the denominator of this is going to be smaller because we are now adding additional predictors. So now the number of variables used is 6. So 25 minus 6 minus 1, so now this is going to decrease by 2 because we have added 2 variables into the model. And the denominator, as we said, does not change. Okay, and so what we see then is that this, now it's clearer to see now that we're dealing with actual numbers, we see that this numerator is going to be larger than this one. Okay, and why is that? Well, because the 10 went down to 9.8, which is a very small decrease. Okay, so this is like a 2% decrease, but then 20, the residual degrees of freedom went down to 18. Okay, so this penalizes the fact that the sum of squares residual only had a small decrease, but then the residual degrees of freedom actually had a larger decrease of 10%. Okay, and so if you calculate this, it comes out to, I think, around 0.347. Okay, so R squared goes up, but then R squared adjusted goes down intuitively because the change in the sum of squares residual by adding these additional predictors is too small. And I believe if you were to do an F-test, you would also conclude similarly that the reduced model is plausible given these statistics compared to the full one. Okay, so just to remind you here, let's make a note here. So n, in this case, n minus k minus 1 is the degrees of freedom of the residual in the reduced. And then here, n minus p minus 1, because we're dealing with 6 predictors, would be the degrees of freedom in the full model. One other thing to notice is that if if the number of observations is extremely large, so if n is like in the millions or close to infinity, then clearly R squared adjusted and R squared are going to be it's going to converge to R squared because you have in one denominator you have n minus 1 and the other one is n minus k minus 1, right? So if the number of observations is very, very large relative to the number of predictors that we have available, then R squared adjusted and R squared will essentially give us the same results. But in practice, of course, we calculate these because in practice we often have a limited number of observations or in sample size from which to fit our model. So these can be quite different, especially for smaller sample sizes. Okay, so here we have only 25. So we have R squared adjusted, and then as sort of alluded to, we also may want to calculate the estimate for sigma squared hat. So what's the estimate of the residual variance? Okay, so as mentioned, it is in fact just this expression up here, right? Because this is the sum of squared residual divided by the degrees of freedom of the residual in the respective models. Okay, so using that fact, then we know that the estimate of sigma squared is 10 over 20, which is 0.5. And then in this case, we have 9.8 over 18 as the estimate of the sigma squared hat, which is actually, as we pointed out, is actually larger, 0.544. Okay, so remember, sigma squared hat plays a role when we want to do prediction. Okay, so which model actually going to give us tighter confidence intervals when we want to predict the response, given a bunch of explanatory variables? Well, actually, the simpler model is going to do a better job, according to that metric. And in fact, so let's say a couple remarks before we move on from adjusted R squared. Okay, so let's make a couple of remarks. So the first one is what I sort of said verbally before. So R squared adjusted, as we showed, is going to be less than R squared because of the penalty for the number of variables we include. But if we have a whole ton of data, so as n goes to infinity, it's going to converge. Okay, but in practice, of course, we're going to have a limited sample size for learning our model, and so we can so this can be quite useful in practice. For example, when in this case, indeed, R squared adjusted went down quite a bit when we threw in two relatively unimportant variables for predicting the response. Okay, so that's the first remark. And the second one is that R squared is very much tied to the residual estimate of the residual variance. Okay, and so from this we learn, because this numerator is the estimate of sigma squared for the particular model, so that means the two are directly tied together. Okay, because the denominator here, the sum of squares total part, is not changing. Okay, so what we can say then is that the model with the higher adjusted R squared, okay, must have a lower, has the lower sigma squared hat. Okay, and so therefore we see that this metric, R squared adjusted, is actually very much tied to the ability of the model to produce precise prediction intervals. Okay, so higher R squared adjusted will give us tighter prediction intervals when we use the model to predict on new data. Okay, and therefore is a reasonable. Okay, so this justifies. Thus is a reasonable metric for model selection. Okay, so that's adjusted R squared. Okay, so it provides a reasonable metric because if we pick the model with the largest adjusted R squared, that in effect also gives us the model that will give the most precise and narrow prediction intervals for new data. Okay, so I also want to give other examples of selection criteria, especially two that have had a very important role historically in statistics and are still widely used. Okay, so the first one was R squared adjusted. The second one is AIC. Okay, so this is named after Akaiki. It's called the Akaiki information criterion. Okay, so it's usually abbreviated as AIC. Okay, so this one comes at model selection from a maximum likelihood perspective. So let me explain what it is. And we'll see it has some common themes as R squared adjusted in the sense that it also penalizes including too many spurious parameters. Okay, so suppose, so let's n be the sample size, so the number of observations we have for fitting the model, and let's say q is the number of parameters. Okay, so I'm giving you the general definition. So what is Q in the context of multiple linear regression? Well, so in multiple linear regression, we have, let's say, it would be k predictors plus 1 for the intercept, and then plus another one for sigma squared. Okay, so it would be, so in multiple linear regression, this would be the number of predictors plus 2. Okay, the 2 comes from the intercept and the residual variance, which is also estimated. Okay, and so in general, the AIC is for the model is defined as 2 times the number of parameters, so 2q minus the 2 times the natural log of the likelihood function evaluated at theta hat. Okay, so let me fill in what this means. So what is this guy? This is the likelihood function. Function evaluated at the estimates. Theta hat, which is the estimate parameter estimates. Okay, so in this course, we're not focusing too much on likelihood methods. Although you probably heard the term maximum likelihood from other stat courses. What we want to point out here is that the reason this is AIC is relevant is, as we sort of alluded to, but I want to restate. So note that the least squares estimates for our regression parameter, so for beta, and as we showed, the least squares estimates for the betas, they follow a normal distribution from which we get confidence intervals and so on. Okay, so the least squares estimate, so beta hat calculated based on the least squares optimizing criterion is equivalent to the MLEs. So the ones you get from maximum likelihood under the usual normal assumptions. On the error terms, so on the epsilons. Okay, so therefore it's it's not far-fetched to use the AIC in relation to model selection. Okay. Okay, so where does the penalty come in then? Well, it's this part. Okay, so this part, the 2 times q. So you notice the more predictors you add in the model, then the larger this first term will be. Okay, so this is the penalty for including more predictors. Okay, so that's this term 2q. I should also point out that with the likelihood function, when you use more parameters, so it's similar intuition as when we did R squared adjusted. When you throw in more parameters, well, the likelihood function will increase. Okay, and so if this increases, then you're taking the minus of it. So log is a monotone transformation. So therefore, if the likelihood function increases a lot, therefore the AIC will decrease. Okay, so the decrease in the likelihood function is offset by this penalty term. Okay, so this is going to go. This is going to increase by throwing in more parameters, but you're hoping that by throwing more parameters, the maximum likelihood is going to L theta hat will increase a lot, and therefore this minus term will offset this penalty. Okay, and so let's talk about its interpretation. And so, okay, so let's just say that in words what I write down. So with more parameters, the likelihood L theta hat increases. Okay, so this is going to become more negative, and it's offset by the penalty, which is 2q. Okay, and so what this tells us is that lower the model with the lower AIC is better or preferred. And what really matters is the difference between AIC values. Okay, so the absolute value, I mean the magnitude of the AIC is not interpretable. It has to be interpreted relative to AICs of other models. Okay, so the difference is, so in other words, it's the differences in the AIC matter. Okay, so you can't interpret not the value in isolation, not value itself. Okay, so we're always comparing. We'd always be comparing AICs of different models. So similar to the R squared adjusted, you fit a whole bunch of models and calculate all the AICs, and then according to this criteria, you would choose the one with the lowest AIC. So lower is better. Related to that is also BIC. And there's actually a lot of other information criteria. Probably most famous is AIC, and there's also BIC. Nowadays, you also have DIC, you have WAIC, you have LUIC. So you have there's been a lot of recent research that tries to improve on these criteria for a specific situation. But we just mentioned the two most famous ones, AIC and BIC. Okay, so BIC stands for Bayesian Information Criterion. And so it's similar to the AIC, but it uses a different penalty term. but stronger, but more strongly penalizes inclusion of more variables. Okay, and so the BIC formula. So here you have 2 times Q. In BIC replaces the 2 with the log of the sample size. So natural log of n times Q minus the rest is the same, minus 2 times natural log of the likelihood. Okay, so the difference here is this part. Okay, so the more data you have, the more strongly having too many parameters is penalized. Okay, so this part is dependent on the sample size. Okay, so just to summarize, so I've given you 3 examples of metrics that we could use to select between different models, and what we could say is that, to summarize, the large adjusted R squared is preferred, and then small values, so the lower values of AIC and BIC are preferred. And there's no hard rule for when you should use one criterion over the other. So it's often we can look at different criteria depending on the context. So there's many. So the key message is that there's many metrics that are available to help us determine which final model to go with. Okay, so here's sort of a recap note about all these. So R squared adjusted, AIC and BIC. They are all based on comparing the fitted models. In other words, they look at how the explanatory power of the model. Okay, so we call it explanatory because it's based on the fitted model. And also also common to these types of criteria is that they all have penalties. Penalty terms for including too many variables. Okay, so why do we want to avoid having too many variables? Okay, so let's talk about that as a conceptual and intuitive point. So the key idea, which I'll put up front, all the penalty terms to try to prevent overfitting. Okay, so what is overfitting? It's the idea of having too many variables. And so when you have too many variables, you might be considering relationships between variables that are actually spurious. Okay, so you might actually be modeling spurious relationships. So when it's actually just noise, you basically taking the case where there's actually no relationship between some variables, but you overfit. And so so in words, you're modeling spurious relationships that are actually noise. Okay, and so what's the downside of that? Well, we already talked about one, which is the lack of interpretability when you have all these variables in a model that actually don't really affect the response. But more importantly, your model could actually do very poorly when you try to use it for prediction. Okay, so imagine you have a bunch of variables in your model that don't actually really affect the response. So you've used them to fit your data, but in fact they're in there without actually having a general relationship with the response. Then what will generally happen is when you now use your model and you try to do prediction on new data, you're going to have a high error. Okay, and so by way of mentioning that, we have other types of criteria that are based on assessing how well the model does on new data. Okay, so that contrasts with these criteria, which are based on the model fit. We can also look at criteria that are specifically focused on the model's predictive performance. Okay, and so I will just briefly mention that now. We will look into that in more detail when we look at, for example, cross-validation. Okay, and so the 4 is back to model selection criteria. Is we could do something like the mean square prediction. Okay, so you can abbreviate that as MSPE. So the idea is that consider the predictive performance of the model on new data, which is in the sense that not used data not used in the fitting of the model. Okay, so this is also known as, let's say, out of sample performance of the model. Okay, so in other words, this is asking whether the model we fit is whether it's generalizable to new data. Okay, so the key question is the model generalizable to new data. Okay, and so this is another kind of strategy to prevent overfitting. Okay, so what happens if if we're spuriously fitting the too many predictors to the model? Well, it's not going to be in general. It's not going to do very well when we then test the model on new data. It may have picked up noise where there was actually no relationship, and so if it's modeling the noise that where there's actually no relationship, then the error when you try to do prediction if you hold back part of your data for this purpose of assessing prediction error, then overfitted models generally will do poorly. Okay, so we'll just mention this conceptually for now, and we will see in the coming lectures specific applications of this principle. Okay, so so the key here is overfitted models tend to have a high prediction error. Okay, and so examples of schemes to do that, which we'll talk about in subsequent lectures, is, for example, by cross validation. Techniques as a way to assess model performance on new data and their generalizability for doing prediction. Okay, so I think we will call it a day here. I do want to mention one last thing. So, okay, so those are all examples of okay, so the above, so just to recap, we've given 4 examples of metrics or criteria for comparing models. But just as by way of preview, the search strategy is also important. Okay, so imagine we have let's say P predictors. Okay, so how many let's just do a quick count so that we see why selection and search strategies are needed. So we have P predictors. We're going to have, well, how many regression models have one predictor? Well, if you choose one of them, so you're going to have P choose one. So that's P regressions with one predictor. And you have P choose 2 for 2 predictors, all the way up to P choose P with P predictors. So we put all these together. Then what we notice is, well, how many potential models are there? Well, we'll see that it grows quickly. It grows very fast. Okay, so the potential, so the number of potential models would be the sum of all of these. So if you add up all these binomial coefficients, P choose J. Okay, so these are all the possible regression models. This is how many there are, based on us having a total of P potential predictors. And so by property of these binomial coefficients, we sum P choose J from 0 to P. That is in fact just 2 to the P. And so this, as I mentioned, grows very fast. So if you had 100 predictors, you would have, if you wanted to test all of them, you would have 2 to the 100 models, and that's infeasible, even with what we have in terms of modern computational power. so there's that. So there's this issue in terms of the feasibility of being able to fit a large number of models. So that's why we'll need search strategies. But also in terms of interpretability, as we mentioned, we like simpler models. And this is not a new idea. In fact, it's very old, and we may have heard this term. So the principle is that simplest explanation is usually the preferred one in the setting. So this simplest is so this is just a rough paraphrase. Most likely the right one. Okay, so this sort of principle has been applied in many scientific fields, and it's known as Occam's razor. So this is why is it Occam's razor? Okay, there's two parts to it. There's Occam, so it's clear that's named after a person. Okay, his name is William Occam, who lived in the 13th and 14th centuries. Well known as a philosopher and also a theologian who studied scripture. And he had he stated in some of his writings what he would consider truly necessary entities, and so later this sort of idea of taking the most simplest explanation possible. So when we apply it to statistics in particular, it's the simplest model with the fewest number of predictors that can adequately explain our data. And so that's first term, Occam. So why do you call it razor? Well, it's actually quite simple. I mean, you use razors to shave things away, and so in essence, the principle of Occam's razor is to shave away or to cut all the unnecessary assumptions in the building of our models. So overall, then, in this today's lecture, I've given you some metrics for determining what is how can we decide what's the best model. And so there's reasons of interpretability, there's reasons for predictive performance, and also philosophically, it's also based on the principle that we prefer the simplest model that we can fit, that can do the best in terms of predicting the response for potential new data. Okay, and so next time we're going to come back and look at this idea of, well, how are we going to actually search through the space of models? If we have a large number of predictors, well, clearly we cannot test all possible models. Okay, and so either we can use some sort of deterministic methods like stepwise regression, or we can do that sort of search in a more stochastic way. Okay, so with that, I will call it a day, and if there are any questions in chat, I will answer them before logging off. Okay, so there's a question: does the individual value of adjusted R squared matter, or is only the difference that matters? Yeah. So as a matter of model viewed from model selection point of view, then yes, it is the difference that matters, because as we mentioned, the adjusted R squared already loses the clean interpretation of R squared as a measure of the amount of variance explained by the model. And so when we have a whole bunch of R squared, I mean, and also as a general point, right? What's considered a high R squared in general? Well, it's actually very much discipline dependent, right? And application dependent. For example, in the social sciences, it's actually, because they involve often human subjects, R squareds can tend to be quite low. Okay, so often regressions aren't going to be able to explain very much in the response, whereas in applications sort of like engineering, R squareds can be quite large because we're dealing with physical phenomena. So as a model selection criterion, using adjusted R squared, we primarily just need to focus on, yes, the relative differences between models. Okay, so if there are no other questions, then we're going to pick up on this. I'll be back on stream on Wednesday, and then next time I'm going to focus on search strategies. So how we can find the best model possible when potentially there are many competing ones. Okay, so we'll see you on Wednesday.